Last time we looked at structural isomerism, which, if you remember, was when two molecules had the same molecular formula, so we had the same number of each type of atom present in the molecule, but they got a different structural formula. What we're going to look at today is actually stereoisomerism, which is another type of isomerism, but this time the molecules will not only have the same molecular formula, they will have the same structural formula as well. And the only difference is that the bonds will be arranged differently in space. So again, there are two types of stereoisomerism. The first type is what we would call geometric isomerism, or cis-trans isomerism sometimes. So let's have a look at a molecule that exhibits geometric isomerism. And basically, it'll be a molecule with a double bond in. And so let's look first at... Now, if we were going to name this molecule, remember we name it for the longest carbon chain here, which is clearly just 2 carbons long. The double bond makes it an alkene. So 2 carbons and alkene, that's going to be ethene. But then we've got these 2 chlorine groups. We've got 1 chlorine on the first carbon, 1 chlorine on the second carbon. So this would be 1,2 dichloro ethene. Now, what's special about this molecule is that it does show geometric isomerism, because if I draw the hydrogens and chlorines, instead of being on the same side of the double bond, I put them on opposite sides of the double bond, I've actually produced an isomer. This molecule is different to this one. And the reason for that is the presence of this double bond here prevents rotation. So if this was a single bond, what would be able to happen basically is this half of the molecule would be able, this half of the molecule here would be able to rotate with respect to this half. So basically what you could have is a rotation around there. If that was just a single bond, you could rotate that around and produce this structure. But the double bond, second bond there, prevents that rotation, so it can't rotate around like that. And so this molecule is actually different. And what we do is we call this, when we've got the 2 hydrogens on the same side of the double bond, we would call this the cis isomer. So this would be an example of cis, 1,2 dichloroethene. And this one here, where they're on the opposite sides of the double bond, would be trans, 1,2 dichloroethene. There we are, the cis isomer, the trans isomer. So the only time you have to look out for geometrical isomers is when you've got this double bond. If there's no carbon-carbon double bond, you're not going to have geometric isomerism. They're not going to have these cis-trans possibilities. But whenever you've got an alkene, just be careful, look out where the double bond is, there may be these 2 different forms. What about this molecule then? Could we name it first of all? Well, if we look at it, it's got 4 carbons in. 1, 2, 3, 4, I'll number them there. And so it's going to be but, and the double bond means it's going to be an alkene. And this is going to be butene, and the double bond is on the second carbon, not the first one. So what we've got here is but-2-ene. Now the question is, are we going to have a cis and a trans isomer for but-2-ene? Well, to figure that out, what we're going to do is we're going to draw the structure out around the double bond. So basically here, around each carbon in the double bond essentially has got 2 single bonds and a double bond, which are going to sort of arrange each of as far apart as possible. So what this structure is actually going to look like, around that double bond we're going to have a hydrogen there. And if we look at this part, then we've got this part of the molecule, we've got a CH3 group. So we'll just show that there like that, just to show the kind of the structure of this. And here, this hydrogen will be there. We've got another CH3 group. Now that would actually be the cis isomer. So we've actually got there cis boot to ene on the account of the fact that here we've got the hydrogens on the same side and the CH3 groups on both on the same side of the double bond. What we could actually do is we could form a trans isomer where this time the hydrogens are on the opposite sides of the double bond, and again, because the double bond prevents rotation, prevents one of these carbons bond rotating around this axis here, we can't rotate this into this molecule. So these two are different. There's the cis isomer and there is the trans isomer, trans boot to ene, and there we go. What about propene then? Would that show geometric isomerism? Well, again, let's draw out the bonds that are attached to the carbons in the double bond. We've got a hydrogen there, we've got a hydrogen there, we've got a hydrogen here, we've got a CH3 group there. Would that show geometric isomerism? Well, no, because we need each carbon has got to have different groups attached to it in the double bond here. You know, if we were to draw this out differently, it's the same molecule. Here we could just flip the whole thing over. If we flip this round, we'd actually form this molecule. So you've got to have, here we've got two hydrogens attached to this carbon. We'd have to have a hydrogen and something else here in order that we could have the cis trans isomers. So these two are the same thing. There's no geometrical isomerism here in this molecule. So there is a second type of stereoisomerism, which is called optical isomerism. And one molecule that shows optical isomerism would be this one. So what is that molecule? Well, the OH means it's an alcohol. 2 carbons means eth, so it's ethanol. We've got a bromine on the first carbon. The first carbon is the one with the alcohol group on. So this would be 1 bromo ethanol. And this molecule will actually show optical isomerism. How do I know that? Well, the reason is this carbon here has got 4 different groups attached to it. So if you've got an organic molecule and you want to know whether or not it's going to show optical isomerism, just look at one of the carbons. This carbon, obviously it's got 3 hydrogens attached to it, but this carbon has got 4 different groups. If I ring them, it's got a hydrogen group attached there, it's got a bromine group attached there, it's got an OH group attached there, and here it's got a CH3 group attached. And what that means is that it will have a non-superimposable mirror image. And these 2 mirror image molecules are going to be called what we call enantiomers. And we can draw out the 2 enantiomers if we show the 3-dimensional structure. So what will actually happen in 3-dimensional space, these 4 bonds will arrange each other as far apart as possible. And they'll form what we call in chemistry a tetrahedral structure. And I can kind of show that here. So if I draw out the carbon, what they're going to form, like a tripod structure at the bottom. So if we show the bromine group, it's going to be sort of coming out towards us. I drew that wedge showing this bromine coming out towards us. And the CH3 group will be going back into the screen there behind us. So that's trying to show that that's going back in behind us, and this will be in the plane of the screen, the hydrogen, and the OH as well in the plane of the screen, going upwards. So there what we're doing is we're showing the 3-dimensional structure. We've got this tripod arrangement at the bottom, we've got the OH group coming straight at the top, so There's actually a bond angle of about 109.5 degrees here between each of these bonds. Now if we imagine a mirror here, imagine that's our mirror, and we imagine mirroring this molecule in that mirror, what's it going to look like? Well, bonds that are closest to the mirror on this side are going to be closest on this side as well. So what we're going to have here is we're going to have our CH3 group. Draw it that way around because it's the carbons that obviously are connected and not the carbon to the hydrogen there. And then we've got the bromine. And we've got the hydrogen and the OH and are in the plane. So what we've got here is two non-superimposable mirror images. Could I rotate this molecule around to make this one? Well, no, because if I rotated it around here, what would happen is I brought these bonds round to this side. What would happen is we rotated it round to 180 degrees, we'd end up with the CH3 in that position, and the bromine over here, as we've tried to rotate this one round to make this one, we'd end up with the bromine and the CH3 the other way around when we rotated it around. So these actual mirror images are non-superimposable, and they are examples of optical isomers. If you're trying to think, is a molecule, is an organic molecule going to have optical isomers? Well, just look at each of the carbons. Can you find a carbon on that molecule that has actually got 1, 2, 3, 4 different groups? Each group attached to that carbon is different. If they are, well, then you're going to have optical isomers. Let's see if we can think of an example perhaps of another molecule. Okay, is this one going to show optical isomerism? This is 2-bromobutane. 1, 2, 3, 4 carbons. So it's but, and we've got a bromine there on the second carbon. So 2-bromobutane. Write that down, 2-bromobutane. Is this going to show optical isomerism? Well, remember we're looking for a carbon with 4 different groups attached. Certainly that carbon doesn't have 4 different groups. 3 of the groups are hydrogens on that one. Same thing with this one, it's got 3 hydrogens on, so that's not going to, and this one's got 2 hydrogens on, they're the same group. What about this carbon? Certainly it's got a bromine there, let's ring that. It's got a hydrogen there. You might say, well, it's got a carbon there and it's got a carbon there, but look at the group that's connected as a whole. What we've got there is a CH3 group, and attached on the other side, we've actually got 2 carbons and 5 hydrogens in total. So actually we do have 4 different groups attached here. If I was to draw this out 3-dimensionally around this carbon here, what we would have, the bromine there, the hydrogen there, not drawn that very well, but there we go, C2H5 there, and a CH3 there. And if we imagine our mirror there and mirroring that, what's it going to look like on this side? It's going to look like that. And again, we've got non-superimposable mirror images here produced. We cannot rotate this round to make this one. They're different. And this centre here, we would call it a chiral centre. That's the carbon around which we've got the 4 different groups attached here, producing these 2 non-superimposable mirror images. And that is optical isomerism.